Hello students, welcome back. Let us resume our discussion in section 3. Previously, we defined the determinants of arbitrary order, and here's the definition. It's a recursive definition. How did we do it? We focused upon the first row, A11, A12, A13, A14, and so on, and arrange them with appropriate alternating signs, plus minus, plus minus, plus minus, while multiplying the determinants of the deleted matrices, capital A1Js. First row out and jth column out, where J is going from 1 through n. Now this is a recursive definition because each deleted matrix is n-1 by n-1 matrix. So we are using determinants of order n-1 to define the determinant of order n. In turn, determinant of order n-1 is going to be defined by determinant of order n-2. So it goes down, 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 and where does everything begin? Well, here we go. Determinants of order 2. We just defined using AD minus BC, and we proved everything using AD minus BC because this was simple enough, and that's where everything will start. And if you use this recursive definition and this kind of top row arguments, then you can use same arguments to define the determinants of order 3 using the determinants of order 2. And that's what this thing is all about. Not coincidentally, this is what our textbook author did. Look at the first row, A11, A12, A13, with alternating signs, plus, minus, plus, with all these deleted matrices. So this expression fits this one precisely. So our textbook author defined the determinant of order 3 like this, as a matter of fact. I did a little bit differently here, and that's because this is a little bit more effective computationally, and to prove this and the other are the same, those are just tedious exercises, so I didn't really bother. But in terms of theory, our textbook author's method is superior. Speaking of superior, you don't really have to start at 2 by 2. You can do even better, theoretically at least. And this is what I'm talking about. And 2 by 2, let's use the same argument. Let's focus upon the first row, and then first entry, 1, 1 entry, determinant of the what? Deleted matrix. So first row, first column out, what do you get? Just D. And then B times deleted matrix. This entry, first row, second column out, so what's left is C. So what do you have? AD minus BC, and that's exactly the same as before. Change the color may help you see these things a little bit better. Compare this with that scheme down here. Fits exactly. So we don't really have to start from order 2. We can go all the way down to order 1, which is the same as the real number arithmetic. And everybody knows the real number arithmetic is a starting point from pretty much everything. Analysis, algebra, linear algebra, everything. And it's rock solid. See the beauty of it? However, if you have to prove something, and if you have to go down to real number arithmetic every single time, then that can be rather tedious. So usually it is better to have some head start. So most of the time you're going to start from determinants of order 2 when you have to prove something. As for the proofs, I think all those hard proofs will be dumped over to next videos. So for now, don't worry too much about it. And let's move on to the next topic without proof. Okay, next property. The basic properties of determinants, D1, D2, D3, multilinear, alternating, and identity properties. Multilinear is an extension of bilinear and trilinear. There are n columns now, so we need n linearities put together. Fix all the other columns, and in jth column, let's have a linear combination ax plus by. Then we can separate it out, as you can see in the right-hand side, leaving all the other columns exactly the same as they were. So this is linearity with respect to the jth column, and there are n columns, so it's multilinear, n linearities put together. We'll prove it, yes, but not in this video, in a separate video. Alternating, if I switch two columns, ith and jth, then you have negative of the determinant. Here's an immediate consequence. If those two columns are the same, then even after switching, even after taking the negative, we have to have the same value. So what real value, what real number stays the same after taking the negative? That should be only 0. So here it is. If you see two identical columns, then the determinant is 0. Again, we're going to prove it in a separate video. Next, identity property. And that one, on the other hand, is relatively simple. So let's have a short version of the proof. Determinant of the identity is 1. By the way, let's do a little bit of editing here. Excuse me. Okay. Okay, all right. And here's a proof. Okay, in order to see the pattern, I started with really big matrix, but I think I kind of overdid it. But it's okay. We have dot, 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 but to the minimum. So, okay, we have big identity matrix like this, and let's calculate the determinant. How do I do that? Here, first row, so 1 times the deleted matrix, this one, which is actually an identity matrix of size n-1. And then how about all the others? Well, these are all zeros, so 0 times something is all zeros, so this part is all 0. 1 times something, against no change. So what did you get? Determinant of the identity matrix of n dimension came down to the determinant of identity matrix of n-1st dimension. Clever student will see the pattern already, but let's do it just one more time. Okay, all right. Take the first row, and then 1 times the deleted matrix here, and that's another identity matrix. And how about everything else? They're all zeros. So all this part, they're all zeros, and what did you end up with? 1 times this determinant, so 1 times anything stays the same. So what do you get? Determinants of identity matrix of dimension n-2. Keep reducing, 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 and all the way up to 2 dimension. All right. And that's equal to 1 because we proved it. If you want to be even more precise, then you can do it like this. You can go down to determinant of identity matrix of dimension 1, which is just 1, real number 1. Okay, that's actually a complete proof. A little bit naive, yes, I have to say that I didn't use the mathematical induction to the full detail, but still acceptable. Now let's go to the next section. Next section, we have something really important theoretically. So, what is the first expression here? That's the same as the definition of the determinant. Focus upon the first row and then expand. And this one, very similar, except we switched the indices, row and column. Basically, we are doing that. So we have this kind of thing. Left-hand side, that's the first line. That's the definition of the determinant. You see? A11, A12, A13, A14, all those are coming from the first row. And then we have alternating sign, plus, minus, plus, minus, plus, minus, with all these deleted matrices. The second line, that comes from the column A11, A21, A31, A41, all those blues. Because focus here is a column expression, I use same color through the column, all right? And then alternating sign, plus, minus, plus, minus, plus, minus, and the deleted matrices, A11, A21, A31, and so on and so forth. So what's the difference between first and the second? Instead of using row, I'm using the column. First row versus first column. So basically this thing is telling us that row and column are equivalent in terms of determinants computation, as long as you don't mix it up. You just take the row and keep it up with row, or if you just take column and keep it up with column, it's going to be the same. And of course, the immediate consequence is determinant of the original matrix is the same as the determinant of the transpose, because what's a transpose? Column becomes row, row becomes column. But here, as far as determinants are concerned, columns and rows are equivalent in terms of computation. So determinants of the transpose must be the same as determinants of the original from row-column equivalence. The proof is something we'll have to postpone, but that doesn't mean we can't use it. We will use it. Row, column, they're equivalent in terms of determinant, at least. And we can use that property and create, it's not creating, excuse me, and you can use that property to discuss the row version of these fundamental properties of determinants. Here we have n columns, and with respect to columns we have multilinear, alternating, and then the third property, identities, that's not much because either row or column is going to be the same. Here we can get the row version of D1 and D2. Multilinear with respect to each row, and there are n rows, and alternating with respect to rows. Ith row and jth row switch. We have negative of determinant. So row column equivalence, all right. And then general determinant formulae. What's the difference between this equality and that equality? Here, left-hand side is 1 plus j, right-hand side is 1 plus I, or maybe I plus 1. Here, left-hand side is I plus j, right-hand side is also I plus j. So this one, compared with that one, we have first row versus ith row. Here, first column versus jth column. Let's see, do we have some illustration here? No, not really. Maybe let's go over there. Okay, ith row, instead of first row, I can use any row. As long as you get correct pluses or minuses, it's okay. I can use any column. As long as I use plus and minuses correctly, it's okay. Also, we should not mix up row and column. If you use row, use row. If you use column, row is column. How do you prove it? We have to prove this one first, row column equivalence for first column first. And then these, not too bad as a matter of fact. Maybe we can do it at the end of this video. and we'll be using some alternating properties for that. But at this moment, the conclusion is far more important than the proof, so let's just move on. Next, elementary row operations and elementary column operations. Elementary row operations are usually more useful and something we have been doing for system of linear equations and so forth. But in terms of determinants, theoretically especially, columns are more convenient. But then again, we established this. Whether you use first row or first column, they're the same. So column, row, the same. So all the properties about column, row, they're the same. So if I prove something for elementary column operations, I can immediately leave them all over to elementary row operations as well. First property here, multiplying a certain constant c to entire column, that's the same as multiplying c to the determinant. That comes from multilinear property. Multilinear, so we can separate the addition and we can separate scalar multiplication, or put those together, you can separate linear combination. Next, alternating property, we switch two columns, then we have negative of determinant. Third, if you multiply a certain number to one column and add it to another, no change to determinant. We'll prove that shortly, but what about their row operations counterpart? Multiplying c to entire row, I can take c out, and that's coming from the multilinearity. Now switch one row with another row. We have negative of the determinant, that comes from alternating property. Number 3, if you multiply a certain constant c to a certain row and add it to another row, no change to determinant. The counterpart is the third one. So we'll prove this column version, and consequently the row version follows immediately too. How do you do that? It's easy. First, separate this one using the multilinearity. This is a linear combination, a plus c times that. Now we have two identical columns. Two identical columns, that determinant is always 0. So we have c times 0 here. So this entire part drops out. So what do we have? We have the original matrix as before. So determinant does not change if you do this elementary column or row operation. Multiply a certain constant to entire row and add it to another row, or multiply a certain constant to entire column and add it to another column. Now, how do we use these elementary row and column operations? Are they really important? Actually, we're going to be using that to prove this, and this is going to be rough. Product of two matrices equal to product of two determinants. Okay, the proof is postponed. How about some further properties of determinants? Determinant of transpose is the same as the determinant of the original. That comes from row-column equivalence, so that's trivial. Determinant of product is equal to determinant of the original. Determinant of the product is the same as the product of the determinant. And that's difficult to prove, but we will prove it in separate video. The third one, determinant of the inverse is 1 over the determinant. That's not too bad as a matter of fact, because, determinant of identity matrix is 1, and then this is the same as determinant of A times A inverse, you see? And that's determinant of A times determinant of A inverse. So you can easily prove that determinant of A inverse is equal to 1 over determinant of A. Of course, if this is not 0, well, we have to prove a lot of difficult theorems, of course, but the main part is over, and let's meet again for proofs in separate video. Thank you.